Please recording permission from the meeting host.
Then maybe I can only
I'm good, I'm recording.
Okay,
I'm recording, but then a second person maybe.
Yeah, I will record. Yeah, so thanks very much for joining this workshop. And so first of all, I say that this video will be recorded and send it to IROS workshop organization committee so that they put it on the website so everybody can access it. So my name is Jihong. So you probably have already received a lot of email from me, and I think Dmitry and we met before, and Jeannette, nice to meet you. And then, so I was a PhD student working on deformable objects manipulation through vision. I'm working with Andrea. He's my supervisor, and he's also one of the co-organizers. So I'm currently doing my postdoc at TU Delft with Jens and Miguel from Honda Research. So we think that this is a timely workshop because basically we witness a growing interest of managing deformation in various scenarios in robotics. So we choose this format because we want to actually try something which we want to offer an open discussion area where people can interactively discussing the questions to actually faced to solve the problem that challenges and problems faced in managing deformation in robotics. And so this is actually the third session. That is, so there are previous two sessions. And today the theme is modeling and characterizing deformation. So now I'm gonna pass the control to David, who is the chair of the session. And so David, please.
All right, Jihong, so thanks. Yes, again, thanks to the speakers for joining tonight. You know, just probably a bit historical. A few years ago, it was somehow sufficient to differentiate manipulation from rigid objects with deformable objects. Now, somehow, I don't know if you guys share this idea with me, but it's kind of the hot manipulation topic right now. There's so many in Europe, so many big projects on manipulating deformable objects. There's so many papers, you know, every year on this topic. So as Jihong mentioned, we have created this. It's a theme we call it, and that's why we invite the three of you, because we believe you can contribute to either the modeling or the characterization of deformations, you know, in a general way. So well, today in this workshop, I'm gonna start asking each of you to, as we mentioned in the email, to introduce your work related to the theme. And then we're gonna move to some discussions which we have prepared, and which I hope, and my co-organizers will help me, we can leave a little bit the formality and, you know, the kind of traditional way of answering. So, you know, try to explore and even, you know, go a little bit beyond and be provocative in various aspects. So let's go from alphabetical order. Dmitry, could you please share your screen? And I believe you, Jihong, also made you co-host.
Sure. Let me go here. So you guys can see that, right? Okay, so I'll start. You know, I prepared an overview of the work we've done recently, and I'll put that at the end of this, but in the spirit of having a lively discussion and workshop, I also wanted to talk a bit more broadly first about why I think this area is important and how I personally came to study deformable object manipulation. So, you know, it used to be, like David was saying, that you had to answer this question a lot. Why are you working on deformable object manipulation? This seems kind of hard. It's like a weird niche area or something like that. And so I found I was always having to justify this, but I agree that nowadays it's become easier to say, oh, I work on deformable object manipulation, and other people are saying like, oh, okay, yeah, that's clearly an important problem. But I want to take you back and see how I came to, to say that this is an important problem. And I want to take you away from the applications for a moment, right, which we all know well, right? You know, domestic applications, surgical, the manufacturing, food preparation. We all know that, you know, to do these, you need deformable objects. But that's not what got me interested in this. So actually, what I did for most of my PhD was a variant of this kind of problem. I had a rigid arm, I had rigid bodies in the world, and I had to move them around and manipulate them without colliding with obstacles, of course, and obeying certain kinematic constraints. And this was a nice problem to do for a PhD thesis, and it was a very clear-cut problem, and you could easily set up experiments. You know, we were targeting this topic of getting robots out into the real world when we were doing this. But the more and more I got into this kind of problem, the more I saw that this would be great for a factory, but has pretty much no chance in the real world. I mean, this is not real life, okay? Real life is messy. There are occlusions, there's noise, there's deformation of objects. It's a very different problem from what I studied in my PhD. So as I was nearing my PhD, I wanted to look around. I wanted to try something different that might have some chance of having more real world application and importance. And I quickly found that to do that, what I needed to do, and the field as a whole, in my opinion, needed to do, was to start challenging the assumptions which had guided robotics so far. And these assumptions are still actually very prevalent, despite all the new work in learning and so on, some of which we're doing. We're still really relying on these assumptions, maybe not as heavily. So what assumptions do I mean? What assumptions need to be challenged? Well, I think first and foremost, it's obvious for us, you know, on this Zoom call here, that rigidity is an assumption that we can't bring with us to the real world in many settings, right? But I just want us to appreciate for a second how important and fundamental the assumption of rigidity is, what it actually does for us, right? I mean, imagine taking this messy, complicated real world described by point clouds and noisy sensors and so on, and you reduce it down to a few objects, each of which has 6 degrees of freedom. I mean, this was such a fundamental, important step. It allowed us to do something with robotics, but it's also at this time become a limiting idea, and it's not enabling further development. Same thing goes for having known dynamics models and simple uncertainty distributions. Like, you know, we have some dynamics model and we say, okay, well, I'll put a Gaussian to estimate its uncertainty. Guys, we know that that is bullshit, okay? A Gaussian is not going to describe real world uncertainty, especially for deformable objects. It doesn't even describe it for rigid objects, honestly. So also we're used to dealing with fully actuated systems, low dimensional spaces, minimal occlusion. This occlusion thing, we've been working on it in several contexts in my lab. This is such a huge deal, right? Just assuming that I'm going to be able to have vision estimates that can recognize and localize an object when it's heavily occluded is a really big and often unjustified assumption. So that's kind of what we see as, or what I see as the barriers to enable deformable object manipulation. And I really believe that deformable objects manipulation is not just some niche problem that has some nice applications. I actually believe this problem is what I call robotics complete, in the sense of something being AI complete, meaning that you know, if you can solve this kind of fundamental problem, then you will basically have solved a lot of the most fundamental problems in the field and enable all sorts of different applications. And I think for robotics, deformable object manipulation is that complete problem. It involves uncertainty, it involves learning, it involves planning, it involves control, it involves difficulties in perception, and you have to solve all of them. You can't just pick one. So, of course, I have not done this. My lab has not done this completely yet, but we are making progress, and I want to share some of the recent work we have on that. So on the side of perception, we have, of course, many different methods. I think one of the most important things that we tackled in perception for deformable objects is the occlusion problem, right? There's a lot of methods that work when you can see everything, but we were looking for one that worked under occlusion. So you can see here our estimate remains stable despite occlusions, even self-occlusions, which of course happen all the time when you're folding a shirt, for instance. We also tackled model uncertainty problems. Here we have a bunch of simple models instead of one model, and we trade off, basically switch between the simple models as we manipulate instead of picking one. We have poor dynamics models. Here we have a very poor dynamics model of this rope, but we can still do complicated tasks like traverse this maze. And of course, we are doing this on real robots. It's very, very hard, as all of you know, of course. But we've integrated planning, tracking, and control into one overall system so that we can manipulate around objects. And some very recent work, we're actually trying to quantify the uncertainty of our models, not with a Gaussian, but with some kind of learned method. So for instance, here we're using a classifier so that the planner knows what the model is good for and it knows when it can't be used. So that was just a quick overview of our work. Happy to discuss further on any of these topics. Thanks.
Very nice. Okay, thanks, Dmitry. DJ. Okay, Jeannette, could you please share your screen with us and introduce your work about managing deformation?
Okay, sorry, the typical Zoom problem, being muted. Yeah, hi everyone. Thank you, Dmitry, for the great talk and also the motivation. I like that a lot. I'm not even gonna, try to add much to what Dmitry just said. I think I've been working in the past a lot on picking and placing rigid objects or manipulating them. And the problem of managing deformations or deformable object manipulation is actually quite new to me. So I've been only starting with this a few years ago. And the reason for doing that is very similar to what Dmitry just said. It's a hard problem, and there are many open fundamental questions that are very interesting and intellectually challenging. And that's basically why I got into it, apart from looking at all the applications that are suddenly possible. So the kinds of problems we worked on are also covering kind of the whole spectrum of problems that you need in order to have a robot actually manipulate deformable objects. We have actually focused on just a linear deformable object for now. And very interesting, actually, also related to what Dmitry had, was a work that we did on perceiving this linear deformable object basically despite occlusion. So here's just like one small problem where we have a goal image of some rope, and we want the robot just to basically reproduce that shape. And it has to do so also despite all the occlusions and maybe using a completely different rope that has completely different physical dimensions or properties like friction or thickness and so on. And we wanted to do that all in real time. So I don't want to go too much into detail on this work, but here's maybe another kind of view of the sources of uncertainty in perception specifically of deformable objects. And they are very similar to what Dmitry just already talked about, right? So there's like occlusion by the robot that is currently manipulating this. There's like the weirdest backgrounds, right? There's like, of course, different kinds of rope, multiple ropes, and some clutter. And if you want to manipulate these deformable objects, we have to somewhat deal with all of these occasions, and that was really the focus of this particular work. One thing, maybe like just as like kind of like a comment in between, one criticism we got from reviewers on our work is that our approach is very specific to deformable objects. And I found this comment very funny because most of work on, for example, estimating the pose and configuration of a rigid object is also very specific to rigid object, right? We've represented in a very well-known way with a position and orientation, but somehow the review criticism on this work was like, oh, it's too specific to deformable objects or to linear deformable objects, although it's a very high dimensional state space, much higher than for a rigid object. So that I found kind of funny, and maybe we can pick that up or what you think about that later. Right, so apart from the sources of uncertainty coming from perception, we also have uncertainty in dynamics. And in fact, we in this approach, we used like a state space approach where we first perceived the object and mapped it into an interpretable state space. And then we used the learned dynamics model to actually roll out how a rope is gonna behave and unfold, or kind of like how the rope is gonna move, basically, if we do a particular action, if you pull it at a particular point. And the reason why we learned this dynamics model is not because we have a better model or we are hoping to get a better model that generalizes more, but because we needed speed. We did actually we used a model-based planning approach, and we needed a very fast dynamics model that could be rolled out many times in parallel, and therefore we couldn't use a physics-based simulator. It was just too slow. So this is a learned model, not for generalization, but for speed. And the overall approach this is kind of an overview of this. Is like a whole system. As I said, we have a perception model that maps into the state space, and then we use a learned dynamics model to do basically model predictive control, essentially, to bring the rope into a goal state that may be specified with a completely different rope. And I mean, I'm not going to talk about how we actually do this. Maybe one interesting point is that we use a pre-trained model from simulation, but then we fine-tune it on very few data points in the real world, using actually self-supervision. So we don't have this burden of all the data we need for learned models. And the result is a model that can actually deal with all of these cases that I already mentioned before. All of these occlusions and weirded background and so on. And then we basically get this kind of result that I already showed. So that was kind of interesting, but really it was still, the interesting part here was the perception part and integrating it into an entire system. But we still only manipulated this rope on a plane, right, to reproduce some shape. And the next step we really wanted to do was to think about knotting. I think there's a lot of work, and you can correct me if I'm too like maybe a little too general here, but I think a lot of work is on actually taking knots apart or flattening maybe some pieces of laundry and things like that. And there's some work on folding laundry, but there's also not a lot of work on knotting that actually generalizes maybe to different shapes. So we were interested in this problem, and our approach was to decompose this into steps like the ones you see here, because each step is easier to solve than the whole problem. And we can reuse the motion primitives for each step for maybe different knots that are composed of the same steps. And we learned these motion primitives. And the challenge here was really that the knot would be given as in a topological format. And we wanted to, we can actually, something I learned new, plan in topological space with Reidemeister moves and so on. That is something new I learned about deformable object manipulation. But then how to do that with a specific geometry is the question we had to address here. And this is kind of the approach where on the top level we do topological planning, which apparently is solved. And then we translate that into a continuous motion plan to actually then do this kind of knotting. And here's just an example for how this looks like. again, with the same platforms, and we want to go from a start configuration to this topological goal configuration given a plan. Yeah. So this is going to be presented actually at IROS, and it relies on the same perception method that was a little bit improved for dealing with all the intersections that are now happening. But yeah, there's also a lot of adaptation going on to then the geometry that is the actual result of executing motion primitives, and where we had to deal, of course, with accumulating error and so on. All right, so yeah, this was kind of the overview of the work we did on deformable object manipulation, which is, again, like I just started looking into this in recent years.
Okay, thanks, Jeannette. Now, Pangjia, would you mind sharing your research with us?
Wait a moment. You see my slides? So can you see my slides?
Yes.
Oh, okay, okay.
We can see.
Okay, so yeah, so I also did a bit about the deformable object manipulation recent years. So our interest is mainly about the clothes manufacturing. So this is the big picture. So recently, actually there are many efforts about the cloud manufacturing, like using big data to analyze the demand, and then you can use some traditional automation to fabricate the product. And you also can use 3D simulation and digital design to help you to design the product. For example, recently, the Alibaba, they just unclosed the rhinoceros digital factory. Okay, so our actually are following, actually are similar to what they are planning to do, but we will focus on the manufacturing. Like we hope that eventually we can have a robot which can fabricate the clothes, and then if the clothes is fabricated, then we can have robots also to do some other tasks like on it. So that's why recently we have some center for the transformative garment production. So basically how to turn this idea into some reality. Okay. So actually, but anyway, so for our research, we only focus on very small parts of the clothes related like manufacturing. So we actually work on a task called the clothes assembly. So this is some task we observed in some factory. And as you can see in the left video, this is how the worker is trying to fabricate some shoes. Okay, actually the insole of the shoe. And as you can see, first of all, the worker needs to assemble like several pieces of clothes together, and after that, so actually you can use some sewing machine to just like stitch the clothing together. So that's the case. So what we want to do is, okay, so how can we make the robots to achieve the left task? Okay, so we just first of all we simplify that into something that we can do. Okay, so basically is okay, we think this is some clothes assembly task. So we want clothes with some holes so that they can be inserted into some like pin, and then so uses this pin we can like assemble some pieces of clothing together. So this is actually seems to be simple, but still it is a non-trivial task because the controller must be generalized to many different things like the different types of materials, different number of holes, and the holes may have different tolerance and so on and so forth. So in the beginning, we tried to use some like advanced learning techniques like reinforcement learning or deep learning to do that. But eventually we found that it's difficult because the simulation is difficult for the deformable object. So even after very careful optimization of the physical parameters, so So even though, as you can see, the left video and the right video seem to be very similar, but the simulator still cannot give very good performance in our controller. But that's why we go back and trying to use Visual-servo. And so the idea is, okay, we have some feature or velocity in the image space, and also we want to control the drone space. And for traditional Visual-servo, we know the Jacobian matrix, but for the deformable object, we don't know that. But however, we found that we can use some learning algorithms to learn the Jacobian matrix from the data. So we try to use different methods like using the Gaussian process and neural network to do that. And given more and more data, then we can eventually learn the Jacobian matrix, and then eventually we can perform the Visual-servo. This is actually the main idea we did in the past 2 years, I guess. Okay, so this is some of our results trying to achieve the task we just mentioned. Like this is one material. Okay, it's kind of a bit soft and have 2 holes, and our robot can do that. And then this is another piece of clothes, which it is a bit harder and also have 4 holes, and the robot can still do that good enough. Okay. And we also consider the occlusion because as like Dmitry and Jeannette mentioned, so occlusion is like unavoidable in the deformable object manipulation. So what we did is using some technique from graphics called the simultaneous tracking and reconstruction. Basically is, okay, so I will always trying to track and reconstruct this kind of the point cloud for the underlying deformable object. So even though it is occluded, I can still kind of know where the deformable object is. So this is kind of so we can using some like GPUs and to implement this in real time. So even though I just occlude some part of the object or closing, I can still get the base idea. Okay, this is what we did. Of course, the similar idea can be used, for example, to like fit some deformable objects into some specific shape. Like okay, so fit this one to some curve, or you can like apply that to some 3D object, like just to deform that to some specific shape. And recently, we also ask us one problem. So what if the deformable object is actively moving? So it's not like closed, it's just static. It's passive, like we are deformed according to your movement. So assume that there's some like fish, okay, and the robot want to grab that fish. The fish can move by itself. So human can do that easily because we have very good like grasping and also very good sensor and a very good policy. But for robots, it is difficult. So our idea is, okay, so we just use a shadow hand, and we are going to use one network to represent the interaction between the hand and the fish. So, so here basically is for each finger and for each part of finger, we are going to use one vertex to represent that part. And also we will encode the contact force, okay, in the vertex. And then we are going to design one controller. It's still a reactive controller. The input is some states of this shadow hand, and the output is actually the next state of the shadow hand. And so this is a graph neural network. And then we are going to use the reinforcement learning to train this controller. And we hope that eventually I can get a good result. So this is what we get. So after the learning, we can kind of like accomplish this task, even though not perfect. So this is not a real fish; it's some like a robot fish. And but as you can see, so it is like moving, but my like gripper can still grab that like good enough. So this is what we did, and so that's it.
All right, thank you, the 3 of you. you probably need to specify that in a paper that no fish was harmed in this research. It's kind of, it kind of looks like a real fish. Well, thank you very much to the three of you. Really good work, actually. You are my session, the three of you. I handpicked the three of you for this specific theme. All right. So let's move on to some chat. Okay, so I will first ask some question, and please, even sorry. Let me just very briefly introduce you, my co-organizers. We have Andrea Cherubini in France. Maybe Andrea, can you quickly say hi over there? Andrea Cherubini, and we have Claire Dune from Toulon. All right, so anyone who wants to comment something, the first question and the first thing I want us to engage is related to what we have seen in your very nice work. Is, can anyone share your thoughts on what is, and there's no correct answer for this. So what is, in your opinion, the appropriate dimension that we need to, from a controller, from a robotics point of view, from a sensing computing, what is the appropriate dimension that we need to give to represent the state of a deformable object? We know, actually, all of you show ropes. I mean, I don't think ropes are infinite dimensional systems, right? But still, when we model them, when we want to, actually, all of you are actually doing models and representation of this subject. So anyone, what is the dimension that you can say for, or any way, any method to specify it? Do we, the higher the better? Is there any rule, any approach to, or the smallest number? Is it required? Anyone, please.
Yeah, maybe I can start. I throw in a number, 64. But I mean, everyone agrees. Okay, great. The question is answered, I think. No, yeah, I mean, obviously, as you said, there's no real true, like there is no right answer, right? It depends not only on all the things you said, but I want to add, it also depends on the task, right, that you want to do, how much accuracy and resolution for that infinitely dimensional object do you actually need for that particular task. And also, of course, that's a question of compute you can afford. The lower the dimension, the probably faster, any of the computation you need to do, you can do, but you will pay with some accuracy, right? But maybe for your task, you don't need that accuracy, and that's fine. So it's really, I mean, there's basically no right answer. It really depends. And we didn't have, at least from our lab, we didn't have like a principled method to choose this, right? We chose a dimension for this rope that would just work for our task and would still be real time. That's how we picked it.
Okay. Anyone else?
Yeah, I'll throw in some thoughts. So I agree with Jeannette that it's really task specific what model you want to use. I think this idea that, I get the model in capital letters of the object, then I do control planning, perception, blah, blah, is one of those antiquated assumptions that we need to move away from. To me, there is no such thing as the model of a deformable object. There's just a potentially useful model. And so in our work, what we do in some cases is have a bunch of potentially useful models, and we kind of pick whichever one seems to be working around this current part of the task, and then go with it until we need to switch, basically. Also, there's some exploration in there as well. But yeah, I think one of the things that we have to realize, even though deformation is in principle incredibly complicated, a lot of the times what we're trying to do with a deformable object is ridiculously simple. Like just drag it along a surface or fold it in half. We don't need incredibly complex models for this, right? I think that we have to get away from this idea of, I have the right state, then I will act, right? Or I have the right simulator, the right dynamics, then I will act. And it's more about, I'm acting, things are going well, or maybe they're not going well. How do I adapt? That's the way I look at that problem.
Yeah, I very much agree with you. You know, I kind of, because I see very often in papers that I have to review that. You see, I always have a deformable object at hand when I need to explain something. I literally have it just next to my desk. So when I review some papers, there's very often that, as you mentioned, there's very simple tasks. I don't know, just simply doing like this. And then the authors, they propose a super high dimensional neural network with God knows how many parameters just to fit this. I don't know, but this is simply an implementation of a validation of their method. But yeah, I also have that feeling. Panya, is there any, I mean, based on the work that I know you've done, any specific tasks where reducing the dimension, aka using, for example, PCA, might be useful for?
Okay, so actually, I think basically is that, okay, so my idea is that, okay, so of course you can choose the dimension of the task you want to solve, but sometimes, so actually because we are using robots, the robots actually they can manipulate the object, right? So sometimes we can use some special policies to significantly reduce the dimension of the deformable object. So for example, you can pick a piece of clothes, and if I really want to, for example, to move some points on clothes to some like target positions, I can just stretch the clothes, and then the parts between my fingers will become a rigid body. So then the dimension of that part, which is really important for my task, becomes 6-dimensional. It's no longer like an infinite dimension. So, and another example, maybe we can use gravity to have a strong control of the shape of the clothes. And so in this way, we can also actively choose like what kind of dimension I want to use.
Yeah. Super quick, Jihong, I mean, you're not a speaker, but I ask it because you also have something to say. Any case where reducing the dimension of the object to smaller than the controllable robot degrees of freedom might be useful?
Any case, what do you mean?
Yeah, any situation.
So to reduce the dimension of the control degrees of freedom?
Of the object.
I mean, for me, a lot of cases, it's extremely useful. Like when you try to fold clothes, you put it on the table instead of fold it in the air. I mean, in this case, the table has constrained your degrees of freedom, let constrain the clothes on the plane. And I mean, this is one example, but I think in general, we as human use a lot of, for me, like one thing that I'm really interested in is to explore in experimental contact, such that it constrains some degrees of freedom to reduce, and then reduce degrees of freedom of the object, such that, but I'm really, I was not thinking about this, but Panja just mentioned with, actually you can, with if you stretch the cloth, actually you can make a deformable object rigid simply by stretch. This is something I haven't thought of, and I think it's really nice, and I haven't thought of this before. But the one thing is that when you stretch, one thing I could ask you is that when you try to stretch it, it's possible you break it when you have a cloth stuff.
He proposed a method for directional rigidity. That's how you call it, right? Somehow.
Somewhat, actually, yeah. It's kind of related, but what I was thinking of in this discussion is actually the work of Devin Balcom. I don't know if you guys are familiar, but he did a lot of work on exactly this, that you take a deformable object, you say, it's too hard to like deal with the deformation, and you stretch it out in a particular way. It's not trivial. And then you can manipulate it more efficiently. So that's what came to mind for me.
Okay. All right. So this, I don't know how many times all of us have said the word model tonight, this afternoon. Model. Another question, what do we mean by model? You know, there's, depending on the field, a model, I was talking to a mechanical designer this morning, and I was telling him about a model, and I was referring to a mathematical model, dynamical model, and he was in his mind thinking of a SolidWorks model. In the case of you know, people in medicine, a model is a rat or something like that. Anyway, but in the case of a deformable object, in your work, in your experience, what should a model, what is the best way? I mean, again, best. What models, what type of models should we use? I'm going to give you options. Geometric models, which might include, I guess, somehow directional rigidity. Mechanical models, discretized mechanical models, finite element model, data-driven models, which they don't necessarily need to have a physical interpretation, or any other model. Anyone wants to give your thoughts on this?
Yeah, well, just to point something out, David, so you're saying there's all these different meanings of the word model. And as you were saying them, I was like, well, you know, these sound all really different. Why do we keep using the same word, right? What is it in our language that's, you know, compelling us to do that? And I think one of the reasons that we use the same word for all the things you described is that they're not real, in the sense that they're idealizations or approximations of the real thing we actually want to be doing, right? Just like the rat is an approximation for a human in some sense, right? In the medical world. And to me, the question of which model do you use is less about the specific representation, though I agree there's all these trade-offs, and it's an interesting point, but my question is always, okay, you move to this idealization, whether it's data-driven or it's geometric or it's physical, whatever, great. You move to this idealization, that allows you to do planning, control, whatever. What happens when it's wrong? Because it will be, because it's an idealization, because it's an approximation. If you're really operating in a somewhat open-ended environment that you can't control very well, your model will be wrong. And so to me, the key question is, how do you detect when that happens, right? Because that can be hard. And what do you do about it? How do you adapt online? I know, David, a lot of your own work about adapting Jacobians from online data is directly looking at that question, right? So I will say, though, as a caveat, some models are more adaptable than others. So for instance, take neural networks, right? It takes tons of data to train them. You get some data online, but if you just try to, you know, pump that data into the neural network naively, you're going to get catastrophic forgetting, where you start forgetting what you learned on the big data set so that you can overfit to the new data you're getting. So, you know, that representation makes adaptation harder. Whereas if you use something like a Jacobian, you know, you update the numbers in the Jacobian with little data, it's no problem as long as you don't take huge steps when you update, right? But on the other side, the representation is much more limited to this like linear transform, right? So I think those are the questions we have to ask as we apply these models. And yeah, I don't think there's like a global best one. It's really like, how much do you need to adapt, and is the model sufficiently descriptive for the kinds of tasks you're doing?
Anyone wants to add anything to this?
Yeah, I can maybe also comment on this. So yeah, I like what Dmitry said, that actually the reason why we use model is because we know it's only an approximation. And well, that first of all means, I guess we have to pick a model for, yeah, we have to pick a model for those parts that we actually, or maybe those parts in our problem are adaptable, that our current models are most wrong at. So that's kind of maybe where we are back and forth and like trying different things. And then I also like what you said, Dmitry, about like, yeah, that, and the other thing is that because we use models, they will be wrong, and we need to know when they are wrong, and maybe how likely they are going to be wrong when we use them. And maybe another point I want to make is that apart from the model being the accuracy of a model, we also care about how fast we can basically compute use it for computation, right? So as I mentioned, like briefly on one of my slides, for example, we used a dynamics model for the rope, but it was learned not for improving accuracy. In fact, it's a little worse than the simulator, but for speed. And it's acceptable to be a little worse because we are faster, we can actually use it online and replan very quickly. So that's maybe another place where you really want to use a data-driven model in this case instead of an analytical model. Yeah, and in general, the way we deal with model error is really by by not caring so much about the accuracy of the models that we use also for perception, but rather making them fast so that we can take feedback into account continuously. So to potentially adapt then and recompute plans.
Yeah. Some problem that I have when talking with control people is many of them, not everyone, but they sometimes don't distinguish that the model, whatever we mean by that, is different from the system they are trying to represent. They say, why it doesn't work? I mean, you look at my equations, your experiment, because they call us you experimentalists, do what I'm putting in theory. Why it doesn't work? You look at this, I'm proving everything. Yeah, but this is just an abstraction of a real system. So yeah, I mean, we don't have to agree on that. This is going not the way I was thinking. By this point, we're supposed to be fighting with each other, but we are mostly agreeing on everything. So, but anyway, I mean, not all of us need to answer to this question. I have some, because we have little time. Maybe I will ask this question. We mentioned tonight that there's a lot of work on this field that I personally think that we somehow need to start to kind of defining the differences, because it's not the same to say manipulate a rope to like doing, because we have some other speakers like surgery with deformable tissues. There's so many different applications and problems that is somehow inappropriate to lump them all together into one umbrella term as a deformable object. So that's why we created this theme. So I ask you this: is there any? Can you probably name someone or some group of anywhere in the world that you think they're really doing really cool things right now on this problem? Someone, I mean, some collaborator or anyone that whose work you think is interesting, not just interesting, that is they're really doing something potentially impactful in this particular problem. Whose paper are you excited about?
So maybe apart from all the people who are in this call, right, I'm just going to mention those who are not in there. And I think what is particularly interesting right now is maybe a little off topic is all the soft robotics space, where of course you don't use a robot to manage deformation, right? You actually have a robot wrapped somehow in deformable material or being actuated in some way, right? And it's very hard to do, but it also makes some problems much easier. So I'm thinking of, first of all the soft robotics hands that are out there. I'm thinking of Daniela Roth's work and also Oliver Brock's lab, right? And then I'm thinking of more recently of Alison Okamura's lab with the Vine robots. I don't know if you've seen them. They are really cool, and they are demonstrating a lot of interesting applications that suddenly become possible with an inflatable robot that can really go through very like tight spaces. So that kind of space I also find very interesting related to deformations.
Anyone else?
Yeah, I guess the danger with answering this question is like, oh my God, what if I leave someone out that's really good? And oh no. So
probably without even names, so as Janet said, well, no, she did give names, so maybe field wise.
Yeah, I mean, I started doing deformable stuff when I did a postdoc at Berkeley with Peter Beal. So I'm always a fan of like the stuff happening at Berkeley with Peter and Sergey and so on. I think they have some interesting ways to push learning very hard into this domain that you know, really have been transformational. So you know, that's one example. There's a lot of great work happening in Europe that it's almost hard to keep track of all of the stuff in deformable object manipulation. I remember going to a workshop years ago on there was a whole big project on how to cut meat with robots, and had many different PIs from all over Europe, all thinking about how to cut meat. So I'm afraid I don't remember most of the names, though. So I'm sorry if I left those people out. But there's a lot of great work in many different places. In Japan as well, I've seen a lot of work around food service, which is really interesting. Yeah. But actually, I wanted to address the first part of your comment, David, about all the different tasks and how, like, when we publish right now, the kind of way we do it is we talk about, you know, it's like our cool method for deformable object manipulation or something like that, right, is the name of our paper. And yeah, I also get the sense that we can be a lot more specific and can actually start to think about taxonomies more, about what tasks have things in common and what don't, and you know, make it a little bit more specific, because I think the way we do it now is basically just to differentiate ourselves from the rigid object manipulation world, right? But actually our world is much bigger.
Yeah.
And there are many, many different subtasks, some of which are incredibly simple and don't, you know, you basically treat it like a rigid object and it's fine, right? And some of which are insanely complicated, right? And to lump all of those in one title is misleading, honestly. But it's justified because we need to differentiate. But you know, I think we have a hard time seeing the domain of applicability of the methods that we have. It's really hard to test on all these different problems, right? So we pick a problem or two and we run our method on it, and then we say, okay, it's a method for deformable object manipulation, but we have really very little idea of what it can and can't do most of the time. So yeah, maybe what's needed is an effort to really create some kind of taxonomy or some kind of breakdown of, you know, what are the difficult tasks? You know, does it matter what the dimensionality of the object is? Does it matter, you know, what the accuracy has to be? Does it matter what, you know, all these design choices really for the different tasks? And then we can say, okay, well, on this subset, like these methods are applicable and so on.
Yeah, this is one of the reasons why we have proposed this workshop. Panja, something really quick so we can, we're running out of time, so we can kind of conclude. Everything all right, Panja? Any thoughts on this?
Oh, okay. So there are many people working on the like 3D printing, some heart and so forth. So, and I think this is also closely related with the deformable object manipulation. It's very accurate, and also you need to move very fast, and also you need to make sure that the geometry and the material are both like maintained during the procedure. So, all
right, thanks. Jihong, I think we need to conclude now. As your chair, I thank you for joining tonight. I really enjoyed your discussion, and I now pass to Jihong.
Yeah, thanks a lot for the great discussion. I think I learned a lot, and it's really a great pleasure that and I thank you all at this circumstances you are able to join us. And I know that in Hong Kong it's quite late, so it's quite late for both of you joining. So yeah, so I don't have much to say further than that. And then basically what we will do next is basically we're gonna edit the video, and we're gonna of course send it, and we're gonna promote it in different channels. So what we have in mind is the distribution list of robotic distribution list, and then if you know other channels we can promote these videos, these recordings, please let us know. And also, what also we are thinking is that all of these 3 sessions has triggered a lot of good ideas. So it would be nice. So this is what we are also planning to do, is like getting a paper out of this workshop to talk about challenges and outlook of deformable objects manipulation, or in general, how to manage deformation in robotics. And I will hope to invite all of you to contribute to this paper if you're interested. And that's it. And thank you very much. And we will keep in touch. And also, yes, one thing I forgot to mention is that on the real IROS time, we want to also have a live discussion, like live panel with all the speakers, because this is just a session with 3 of you, but we want to have a live session with all the speakers, and you will hear us soon from that as well. So we will try to organize a time when we have a live discussion with all of the people. Yeah, that's it. Thank you.